here's what we're going to do. We're going to draw our circuit. This is a battery. So wires come in and out of your battery. So that's the symbol for a battery. What would that be a symbol for?
Cell.
Just a cell. Okay, so that's good to know. Now, this would have how much voltage?
1.3. Wait, no,
4.5. Why would it be 4.5?
3 cells.
Each cell is 1.5, and there's 3 cells there, so that would be 4.5. But if there's no number, then you count the cells and you multiply by 1.5, and that's what the voltage is. On the other hand, if I want to put a voltage, say I want to put 12 volts, I have to draw 8 cells. That gets kind of tedious. So if you don't want to draw out all the cells, then you just write the voltage underneath it, and you draw 3 cells, and that's kind of convention. So if I have my 3 cells, what I'm going to do now is I'm going to hook up 1 and 2 and 3 resistors in series. Okay, so again, I'm going to call this one 10 ohms, and this one's going to be 20 ohms, and this one's going to be 30 ohms. So like what we talked about before, we've got 3 different resistors that are all in series. And so now we're just going to do the math behind it. And again, the math behind it is super easy. We just follow these steps. The effective resistance is if I yanked these 3 out and I replaced it with 1 resistor, how big would that 1 resistor have to be to pull the same amount of current? And so it's super duper simple. All I have to do is say, hey, I have a 10, and I have a 20, and I have a 30, and that makes 60. So the effective resistance here is 60, because if I'm pushing against all 3 of these, think of it kind of like a tug of war. If all 3 of them are pulling against me, I have to pull hard enough to balance all 3 of them. That's 60. Anybody have trouble with that math?
No.
You hope not, because that was really ridiculously easy. To find the current, again, since I have only one pathway that goes all the way around this loop, since there is only one pathway, then the current is going to be the same everywhere. So I'm going to have the total voltage, which is 12, divided by the total resistance, which was 60. So 6 goes into 12 2 times. We divide by 10 again, we get 0.2 amps. So we have 0.2 amps is the total current everywhere in that circuit. And again, it has to be 0.2 because I can't stick 0.5 through the 10 and then 0.2 through the 20 because it's the same pathway. So the same amount of charge has to go through all sections. So it has to be the same current. Now to find the voltage drop, even though it is the same current, that doesn't say it took the same amount of voltage to go through each one. Who's going to use up the most voltage? The 30. The 30 is much bigger than the 10, so I have to push a lot harder through the 30 than I do through the 10. So even though I'm pushing against all of them at the same time, the 30 is still stealing more of that juice than the 10 is. So to do the voltage drop, what we have to do is, since we have 3 resistors, we have to do V equals IR 3 times. What's going to be the same all 3 times?
No.
The I. We just figured out this is the I everywhere. So I'm going to do that. I'm going to say, hey, I have 0.2, I have 0.2, I have 0.2. What I do then for the R's is I don't stick the total R in there. I use that to find the current and the effective resistance. But this R, I do each individual R. So I'm going to have 10, and I'm going to have 20, and I'm going to have 30.
That's easy.
So 2 times 10, 0.2 times 10, of course, is 2 volts. And then this one's going to be 4 volts, and this one's going to be 6 volts. And if we add those together, what does that add up to? Hey, what do you know? That adds up to 12 volts, which is the total voltage that we had, and that should always be the case. Now,
It's pretty easy.
the numbers I gave you here are nice, perfect numbers that will always work out to nice whole numbers, and so everything worked out great. But sometimes you get numbers that work out to 0.666666666, and you round those numbers. Electricity doesn't really round, but you do because you don't like to write down infinite numbers.
Yes.
And so sometimes you will end up with 11.9 or 12.1 or something like this. Don't freak out if your numbers are a little bit off like that because that just means you rounded too much. In this case, it came out to beautiful numbers because I stuck in beautiful numbers to get beautiful numbers, and it makes it easier. Now, one last thing I want to do is say, hey, what would be the voltage at point A, B, C, and D? Well, if voltage is coming out of the battery here, and I touched a little multimeter, if I touched a voltmeter, and I stuck this end to ground, then it's going to read 12 volts. Now, how much did the 10 use up? If the 10 used up 2 volts, then by the time I got through with the 2 volts and got to point B, now I hooked my little voltmeter up to ground. And what does this voltmeter going to read?
10 volts.
It's going to read 10 volts because I got rid of 2 volts from the 12, and so hey, I'm down to 10. Now when we went through the 20, that used up 4 of the volts, which means by the time we get to part C, and we stick a voltmeter here and connect it to ground, it's going to read 6 volts, because 10 minus 4 is 6. Then when we went through the 30, hey, that used up, whoops, not 60, 6 volts. So if that uses up 6 volts, by the time we get to D, that voltmeter is going to read nothing. And so by the time we get to D, we'll always have nothing, and at A, we'll always have the full voltage, but the amount that breaks down is the amount that breaks down. Does that make sense?
Mhm.
Yeah. This is super duper simple stuff. So I want you to do series today. Tomorrow we'll learn how to do parallel, which is also easy, but it's just you don't get confused if I teach them on 2 separate days, and so that makes it a little bit easier. So today you're going to have an assignment where you have a circuit that's drawn up here, and I give you values to stick in it, and you're going to calculate everything, so you have 4 different circuits to do here, and that will take you 10 minutes, and you'll be great.